Hi, everybody. Hope all is going well and that our study of Calc 2 is progressing nicely. I want to move on to a new topic. We talked about surface area. We talked about arc length. And now we're going to revisit those as well as some other familiar topics from Calc 1, but from a slightly different context, that of parametrizations. So what do I mean by a parametrization? Well, essentially, you might have, you think of, we're used to thinking of y as a function of x, right? You have some nice graph. We're thinking about continuity and tangent lines and area under the curve. And when we do that, a lot of times we consider y as a function of x. But what I want you to picture now is a point on that curve that is moving. And if that point is moving, then I could consider its x coordinate as a function of time and its y coordinate as a function of time. And so we have this picture of a graph given by some Cartesian expression, y as a function of x. But then we also have x and y as functions of time, representing the way this particle moves along the curve. So given this notion of parametrization, what do all those typical issues of calculus look like, right? Equations of tangent lines, lengths of curves, area under the curve, all those things that we've discussed. How do they manifest themselves when we consider parametrizations? So that's where we're going to go next. And to start, we're going to actually revisit just what parametrization is and practice some. We'll start with a review of parametrizations, and then we'll move into its calculus. All right, here we go. All right, so parametrizations of plane curves. So let's say that we've got this particle and it's moving along the ellipse 9x squared plus 25y squared equals 225. Just for review, you might get an idea of what this looks like. This is not the standard form, but if I divide every term here by 225, then we will get this nice standard form. And so I would encourage you to actually do that as we translate this. And so we have x squared over 25 plus y squared over 9 equals 1. So what does this look like? Well, we know that when y is 0, x is going to be plus or minus 5. And we know that 2, 3, 4, 5, when x is 0, y will be plus or minus 3. And so we get this parabola here. And I'm just a little, there we go. Oh, it's horrible. My art skills are less than optimal. All right. So, one way to think of a parametrization, so picture a point here, a particle that's moving along this curve. Think of this particle as casting a shadow. So there's going to be a shadow along the x-axis and along the y-axis. And the parametrization essentially describes separately what those shadows are doing. It's also worth noting that this this ellipse is not a function, right? Y is not a function of x. But when I parametrize as a function of t, now I can consider x and y independently as functions of t, which is nice. So we'll come back to this because, we want to ultimately parametrize this. And what I mean by that is give equations for x and y independently that are functions themselves of time. And then questions like, well, where does it start? Which direction is this particle moving? How fast is it going? How long does it take to get around one time? Things like that. So I will come back to this. So let's start with this one. A particle's position is given by this parametrization. Identify its path and describe the motion. And so, you know, first thing to notice is there's no restriction on t, right? But think about what an ordered pair would be. It'd be t comma t squared. Well, doesn't that look familiar? In fact, if x is equal to t and y is equal to t squared, then isn't y equal to x squared? And we know what that looks like. It's a parabola. Okay. Now, what about its motion, right? I know what its path is, but if I put a point on here, what direction is it going? Well, notice as t increases, what happens to x? X increases and y increases, which means it must be going this direction. So it's a little misleading to put those arrows on the end, but here's its direction of motion, okay? But this one, a cosine t and y equals b sine t from 0 to 2 pi. Well, when we look at this, at first glance, we might be a little bit confused, or maybe not even know where to start. So let me ask you this. X is given in terms of cosine t, and y is given in terms of sine t. Do we know any relationships between sine and cosine? Yes, right? We know that cosine squared theta plus sine squared theta equals 1. So maybe we can take advantage of that. And we can, because look what happens. If x is a cosine t, then that tells me that cosine t is what? Well, x over a. Similarly, if y is b sine t, then this tells me that sine t is y over b. So now, taking advantage of the fact that cosine squared t plus sine squared t equals 1, look what I have. I have x squared over a squared, because that's cosine, plus y squared over b squared equals 1. Oh, so this is an ellipse. And furthermore, at t equals 0, x will be equal to, well, a cosine 0, whoops, not theta, 0, which is 1, and y will be, I'm sorry, a times 1, a, and y is b sine 0, which is b times 0, or just 0. And then at t equals pi halves, well, x will be 0, right, because cosine pi halves, and y will be 1. So what we have here, and I don't really know anything about a and b. I don't even know which one is greater than the other, but got something like this. All right. If you've ever seen Family Guy, I often worry that my ellipses look a little bit like Stewie. So I apologize for that. And if you weren't thinking of Stewie, I apologize that you now are. All right. So I've got this ellipse, And I know that at time 0, my coordinate is A0. So there's my time 0 right there. And then at pi halves, I'm up here at 0. Oh, I'm sorry, I did it again. At pi halves, right, my y is b, 0b. So the direction is counterclockwise, okay? And let me ask you this question. How many laps is this particle taking? 1 lap, right? The period, well, I shouldn't say the period, but once around the unit circle, if you will, right? Returning to your starting point for both sine and cosine, it's going to take 2 pi. So this particle starts at A0, moves counterclockwise, and then stops when it returns to A0. Okay. How about this one? We have A secant t and A tangent t. Well, let's think about this. We know that one plus tangent squared is secant squared, right? And if you look at the way we've set this up, secant t is x over a, and tangent t is y over a. And so if I play around with this, whoops. You can write that. Well, secant squared, that's x squared over a squared. Tangent squared, y squared over a squared equals 1. What is this thing? Oh, it's a hyperbola. All right. And negative pi halves to pi halves. So let's think about what's going on there, right? First of all, it's x squared minus a squared. That's the form. So I know that this hyperbola does something, well, let me not be completely lazy here, but right, it's going to do something like this. Okay, left and right, opens left and right. Now, we need to figure out, so we know it's going to look like one of these sides. We need to figure out what it's doing. Now, I can't plug in negative pi halves, right? Because, right, tangent and secant, for that matter, are undefined. But how about negative pi fourths? So at negative pi fourths, I get an x coordinate. Well, what's cosine of negative pi fourths? Well, it's root 2 over 2. So this is going to be the reciprocal of that, right? 2 over root 2, which is just root 2. And y will be negative 1. And so that's down here somewhere. Now, what about at 0? Well, at 0, x is going to be 1, and y is going to be 0. So that takes us here. Okay? So when it comes time to graph this thing, whoops, silly arrows, it's moving this direction. Okay? And again, I got that just by taking a time and then a later time. All right, let's do some compare and contrast now. So cosine t, sine t, right? When you look at this first parametrization, what does it give us? Well, cosine squared t plus sine squared t is 1. Similarly, cosine squared 2t plus sine squared 2t is 1. Well, we also know that cosine, that this is, the equation of a unit circle. Same with this one. Well, so far they don't look, so far I can't really figure out how they're different. I see the same path, but, and as sine or as t increases, right, we're gonna move counterclockwise, but they're not the same parametrization. Same path, different parametrization. Huh. Well, at this one, at t equals pi, where will this particle be for parametrization 1? Oh, it'll be there. There's t equals pi. What about over here? Well, when you plug pi in, you wind up with cosine 2 pi, sine 2 pi. Oh, that's here. Interesting. What about pi halves at t equals pi halves? Well, for the first parametrization, you're at 0, 1. You're right here. There's t equals pi halves. Over here, the second parametrization, well, cosine of 2 times pi halves, oh, that's cosine pi. Sine 2 pi halves is sine pi. You're there. Interesting. So this 2 has what effect? Well, if you don't see it yet, frankly, even if you do see it, let's head on over to graphing program and see what this is doing visually. All right, so I have my two particles, and they're at 0 right now, time 0. So they're right on top of each other, same location, 1, 0. And I'm going to hit play. The red particle is the first parameterization, and the green particle is given by the second parameterization. So I'm going to let this play, and I want you to make some observations. So what you should notice is that the green one is moving faster, okay? It takes the green 1 pi to go completely around the circle to make 1 revolution. It takes the red particle 2 pi. So if you notice, the green is going to catch, well, the red and the green are going to be back in the same location at 2 pi. That's when the red gets lapped, right? If you think of this as a race, the red is going to finish 1 lap, and the time it takes the green to finish 2. So even though the path that these particles are taking may look the same, they're different parameterizations because one is actually moving faster. I could even, like if I hid this, and maybe I hid one of the particles, right? That just looks, you don't know if that's cosine t sine t or cosine 10t sine 10t. We don't know. But if I show it and then put the other one up, you'll see the relative speeds of these. Okay? Good. All right. So the last thing that I want to do here is go back to that parameterization we started with, right? We haven't parameterized the motion along that ellipse that we had as our motivation problem. Let's do that now. All right, so here are the conditions that I want to impose on this particle's motion, okay? So let's graph it again just to refresh our memories. So we had, right, essentially we converted this to x squared over 25 plus y squared over 9 equals 1. And so we had 5, 3, okay. And then there's our ellipse. Hopefully yours is better than mine. Okay, we want this thing to start at 0, 3. So that means this is time 0. We want it to move clockwise. So this direction. And we want it to complete 1 revolution over the interval 0, 1. So in other words, t equals 0, and then when it gets back to here, it'll be at t equals 1. Okay. Well, a first thought might be to let x be 5 cosine t and y be 3 sine t. After all, we've seen that but this combination gives us that rotation, right? And it allows to move along this path. But why is this wrong? Yeah, at time 0, right, if we were doing cosine for x and sine for y, then at time 0, we would be at the point 5, 0. We want to start at the point 0, 3. And so maybe we should rethink that. In fact, if I want to start on the y-axis, then what should I make my x coordinate? Because now if I want to start on the y-axis, then I need my x coordinate at time 0 to be 0. So what if I did this? What if instead of letting x be cosine, what if I made x be sine? Does that work? At t equals 0, I get x equals, well, 5 times sine 0, which is 0. And y is going to be 3. I'm sorry, I wrote sine. I meant to say cosine. Y is 3 cosine t. So I get 3 cosine 0, which is 3 times 1, which is just 3. Oh, that works. And then let's check at a later point. Let's say pi halves. Okay, so pi halves, x will be 5. Oh, and y will be 0. That takes me to here. Okay, so I'm going in the right direction. Are we good? Well, there's that little issue. This is going to take me, if I use the parameterization I have here, that's going to take me 2 pi to return to where I started, right? 1 revolution, 2 pi. Well, how can I fix that? Well, it's pretty simple. Watch. Instead of t, let's make this 2 pi t and 2 pi t. At t equals 0, we still have 0, 3. But then pi halves, that would really be t equals 1/2. And does that work? I'm sorry, not 1/2. T equals 1/4. Yeah, okay. And so at t equals 1, right, we'll have sine 2 pi cosine 2 pi. So that works. There's my parametrization, okay? Notice how I built it. Thought about where I start and which combination of sine or cosine as x or y would place me in that starting point. I then verified the direction. After that, I then adjusted the speed so that it went around on the interval 0 to 1 as opposed to 0 to 2 pi. Okay. So here we have it. That's a nice review of parametrizations. Of course, you should practice, work some on your own. And the next issue, so you want to have this down solid because the next issues that we're going to address are those related to calculus, right? We haven't really done any calculus yet. So get these parametrizations down, and then we will address those big issues of calculus in the next lecture. Okay, so until then, I wish you happy studies, make all this your own, and I will see you soon.